Hello everyone. In this video, we are going to cover thermochemistry, and that is actually going to go over two parts. So this is part one. I'm going to share my screen with you here. So thermochemistry, this is the study of heat transfer in chemical processes. So basically, chemical reactions proceed. There is an energy transfer. A lot of the times we're really looking at heat transfer for these. Bonds are breaking, bonds are forming, and sometimes overall a reaction releases heat. Sometimes overall it absorbs heat. So we're going to explore that. So just in general, if a chemical reaction gives off heat, where does that heat go? So you could think of a reaction that's going to get hot. Say it's in a body of water. Where it goes is in that water, or more specifically into those surroundings around the chemicals. So let's take a specific example, lithium chloride solid. This is a salt. This is just like the sodium chloride table salt that you guys have at home. We can dissolve this in water. You guys already know that an ionic compound is made up of a cation and anion, and if it can dissolve in water, not all do, but if it can, it'll break up into its ions, and then those end up being aqueous, meaning they're soluble in water, they're floating around. So can you predict whether overall this reaction is going to give off heat or absorb heat? You can't necessarily predict. We can do experiments to measure that, or you can be given a number. And that number is the enthalpy change here, given by delta H. So here we get minus 37 kilojoules. That means that amount of energy is released. So joule is a unit of energy. When you have a negative sign, that means it is exothermic, or heat is released. And this is specific to lithium chloride dissolving in water. So again, other salts, they may overall release heat or absorb heat. What does that look like? Basically, if I put the salt in a beaker of water, I have originally the solid, alternating array of cation and anion. There is a very strong electrostatic attraction between the positively charged and negatively charged ions. So basically, that's what holds that ionic compound together. That is the ionic bond. The way that ionic salts dissolve is basically the water chips away at it, peeling off a cation or an anion, and ultimately the anions are surrounded by the plus ends of water. The white balls or spheres, those are hydrogens, and the cation is surrounded by the negative end of water, the red oxygen end, which is more negatively charged. It has lone pairs. So again, there are some salts that'll absorb energy overall. And where does it get that energy? Basically from the surroundings. So the surroundings in this case is the water. So if they absorb heat from the water, it makes the water feel cold to our touch. These are salts that could potentially be used to make cold packs for injuries. Salts that are exothermic when they dissolve in water could potentially be used to make hot packs. Okay, let me just break this down and introduce you to an energy diagram. Basically, if you look at this flask, we have what's called the system. The system is what you're looking at. The system in our case is the lithium chloride. Everything else, literally everything else, the rest of the universe, the tabletop, the water around it, that is the surroundings. So what we can see in an exothermic reaction is that from the perspective of the system, heat is released. It goes out of the system where it's absorbed by the surroundings. But basically what we could do is have an energy diagram where the y-axis is some unit of energy. Sometimes people call it potential energy or just E for energy. Enthalpy here, H, which is actually heat for a reaction. And what we want to do is just note the different levels of where the energy is of the system before and after the reaction takes place. So basically, if I have this scale, energy is higher as we go up. So in this particular exothermic reaction, I'm at this level. This level is higher than something down here. So before the reaction, I'm at a higher energy. And then as the reaction proceeds, I release energy. And after the reaction, I've given that energy away. So now I'm down here. I don't have as much energy. And you could think of it as potential energy. For example, a basketball being lifted up high, it has the potential energy to release energy as it, say, falls down to the floor. But once it hits the floor, it had given up all its energy. And now it's at a lower energy state. If we look on the right-hand side to the endothermic reaction, basically the system is absorbing heat from the surroundings. The energy level increases, so after the reaction, the system is now at a higher energy. The difference in the energy is this enthalpy change, delta H. Okay, let's look at an example you might be a little more familiar with. Respiration. So basically we have glucose here, C6H12O6, combusting. So you guys have seen this before, reacting with oxygen to produce carbon dioxide and water. What you also see in this is an energy on the product side. So calories is a unit of energy. We'll mainly use joules or kilojoules for this lecture and for this whole thermochemistry chapter, but calories is a unit of energy. The significant thing to see here is that it's on the product side. So what that means is energy is released. So overall in the combustion of glucose, which is respiration, energy is released. When we burn blood glucose, we use some energy to break the bonds of glucose and some O2, but then we reform new bonds in making these new compounds. This is a very, very important concept for you guys to understand, and hopefully we could revisit this over and over. The biggest reason why a reaction is endo or exothermic is whether or not the energy used to break the reactant bonds is greater or lower than the energy released when you form the product. So that's a really key thing here. Every time you break bonds, it takes energy. Just think of two balls held together by a chain or a rope. To break that, you have to cut it, pull it, whatever. You have to input some energy. So effectively, for every chemical reaction, what you are doing is you are destroying the reactants, breaking bonds that will always take energy. And then when you form the new products, now new nuclei are seeing electrons from another atom and you're releasing energy. In our case, we're forming covalent bonds in this particular example. The plus of one atom is seeing the minus of another. And the plus in the covalent case is the positively charged protons in the nucleus and the negatively charged electrons in the other atom. Okay, so in this case, overall, energy was used to break these bonds, but more energy was released when you formed the two products, which is why overall energy is released as a product. Visually, if we tie this back to the energy diagram, here I'm just saying energy in general goes up. Again, this is exothermic, so your starting point is higher in energy and your products are at a lower energy. So this reaction had the potential to release energy. The one thing I want to show you with this special diagram is that this is a hill. What this is reflecting is it takes energy to break the bonds of the reactants. It will always be an uphill climb. Then it depends on the reaction. Sometimes you release a little bit of energy. In this case, we released a lot so that more energy was released when the products are formed. So overall, you have a net release. The difference between here and here, the reactants and products. The delta H is actually the energy of the products minus that of the reactants. So overall, a net release of energy, that is exothermic. What does an endothermic reaction look like? And I did put here, this is delta H, the difference here. Endothermic is the opposite, photosynthesis, and you may be familiar there. If we just reverse the reaction and instead we start with carbon dioxide and water, plants can undergo photosynthesis. They need energy from the sun, and you get your glucose and oxygen. So if respiration looks like this, exothermic, endothermic, the biggest difference is you have a much greater uphill climb because you have to overall add more energy, and then you only release a little bit, but not even enough to make up what you added. So overall, the net is a positive delta H from here to here. So again, it's the energy of the products minus the reactant. So you can see that's a positive number there. Overall, I had to add energy. One way to think about that is, say you have to climb a hill, you put in a ton of energy, maybe you're on a skateboard, but then when you go to the top and you get your ride down, you barely get a good ride, you don't release as much as you put in. Okay, so just visually be able to recognize, just by looking at a curve, the difference between endo and exothermic, and then also how to calculate delta H's. So I could show you that here. So here I put exothermic on the left, so potential energy increasing as you go up, but the reactants here, high in energy. When you get down to the products, heat is released. So the difference between these two. And again, it's the energy of the products minus the energy of the reactants. And the reason why it ends up negative with exothermic is the product energy is a smaller number. So a smaller number minus a bigger number, you get a negative delta H, exothermic. Opposite for endothermic, reactants are down here, and overall you gain energy as you go to the products. Okay, let's step back a little bit, take a look at the first law of thermodynamics, which says that the energy of the universe is constant. So this is important for us because we study heat transfer when we look at thermochemical equations, when we look at objects giving off heat to water, for example. So basically what this means for us is heat is not lost. Heat is not created nor destroyed, just like mass. So basically any change in energy of a system is equal and opposite the change in energy of the surroundings. So let me just give you an example you're familiar with, a pot of boiling hot water. If I took that pot and I put it on the tabletop, what's eventually going to happen over time? Basically, it's going to cool off, right? Where did that heat go? Some of you might say the tabletop, right? You've seen that before. Maybe you've had a plate or something, you feel the table underneath is warm. Maybe the air surrounding it. All of that, everything other than the system that you're talking about, everything else, that is the surroundings. So the heat given off by that system is the exact same number of, in terms of heat and energy, as that absorbed by the surroundings, and vice versa. If it was actually the system that's absorbing the heat, it's absorbing the equal and opposite amount of the surroundings. Okay, what makes up energy? There are two components, heat and work. So heat is given the symbol Q. This is thermal energy. This is the heat transfer that we'll talk about when reactions are run, when an object transfers heat. So basically, a hot body will transfer heat to a cooler body. Work, that's the movement of an object. So in chemistry, we see work in a couple different ways. We see a gas expanding, and we also see it with the movement of electrons, so creating electricity. One that you've actually seen recently is in your copper cycle lab. You guys took copper wire and you guys treated it with nitric acid and you saw a gas evolve. So basically, here I have a copper penny. I'm going to put it in nitric acid, but instead of doing it in the hood where you guys saw that brownish yellowish gas evolve, I'm going to cap it here with the stopper. And the stopper has a tube that goes into the cylinder that has a piston that can rise. So basically, we're going to do this reaction that you guys did in your lab recently. So I'm going to create nitrogen dioxide, that's the gas being evolved, and now that gas is going to fill the container. It's going to proceed through the tube into the cylinder, but now the gas is going to expand against that piston, going against that atmospheric pressure, and it's going to do work on the surroundings. So basically, the atmospheric pressure, this is due to gravity and the air molecules above us pushing down. So it's working against that pressure. So work is going against that pressure, so it has a minus P, and it's just times the volume, that change in volume. That's shown here. So I don't need you to do any calculations of work, but I just wanted to show you where that comes from. Okay, let's forget about work. If we only look at Q, which is actually more relevant to us because that's most of the reactions that we look at don't involve work. So if we only look at heat transfer, we call that energy change enthalpy, and it's given the symbol H. So when a reaction is run, you can actually calculate the heat transfer. We give that number, a delta H, based on the equation written, with the stoichiometry written, and it gets a number. Here it's negative, so we know it's exothermic, and it gets a unit. In this case, it's kilojoules. So here heat is released, exothermic. Just to remind you, a positive delta H is endothermic and heat is absorbed. What can we do with this information? We can do a lot, actually. So sometimes you'll also see this for a reaction, this little subscript AHxn for enthalpy of reaction. Sometimes it's there, sometimes it's not, but basically it's the enthalpy for the reaction as written. This type of equation is called the thermochemical equation, just because there's some thermochemical information associated with it. Here's something interesting. What if I completely reverse the reaction? So instead of taking H2 plus O2 to give water, I'm going to reverse it. So 2 waters proceeds to decompose into 2 hydrogens and 1 oxygen. Look what happens to the delta H. The sign changes. So if you do the reverse, remember, this is all about bond breaking, bond forming. So if you do the reverse, you get the opposite sign. Does that make sense? If I run this reaction, I have 2 hydrogens plus 1 O2, giving 2 waters. That means I destroyed or broke 2 hydrogen bonds, broke an OO, it's actually a double bond, and then I formed actually 4 HO bonds, because there are 2 HO bonds in 1 water, but I have 2 waters. So basically, overall, when I do this process, the formation of this water is significant and leads to an overall release in energy. But if I flip everything, destroy water and form these guys, then overall, I have the same number, but it's endothermic, the positive. What can we do with this information? We can calculate the heat transfer for any amount of any of these substances. So let me just walk you through this equation and the way that we use this. This equation says that 2 moles of hydrogen plus 1 mole of O2 gives 2 moles of water. When this occurs with this number, 2 moles of H2, when 2 moles of H2 react, this says 572 kilojoules is released. But what if you don't have 2 moles? What you're going to do is use delta H and whatever stoichiometry you're looking at, like mole ratio. So let's just look at this problem. How much heat is transferred? So I'm not telling you if it's absorbed or released yet, just how much is transferred when 3 moles of H2 react with excess oxygen. So what I do is I just start with the 3 moles and I look at the equation and I can see, using this like mole ratio, for every 2 moles of hydrogen I react, I release this much energy. So just like mole ratio, I put the 2 moles of H2 on the bottom to cancel moles of H2, and then minus 572 kilojoules on top. Notice I carried the minus sign. This is important because at the end, it'll tell you if heat is released or absorbed. Crunch the numbers, I get minus 858 kilojoules. Heat is released. Okay, you guys practice this one. So pause it and then work this problem, and then I'm going to explain it. So this question is, what is delta H, the enthalpy change, when 16 grams of oxygen reacts with excess hydrogen? So this is not a limiting reactant problem. It's saying you have plenty of hydrogen to complete this, but you do have 16 grams of this. So the only way we can do this problem to figure out delta H is, again, use this like its mole ratio. So we need to get into moles. I start out with what I'm given, the 16 grams of O2, and then I go grams to mole. I use molar mass. And since I'm talking about O2, I get the mass of 2 O's. 16 plus 16, I get 32. And so 32 grams per 1 mole of O2. It's always per 1 mole for molar mass. Doesn't matter what it says up here or what it says here. And then now I'm in moles of O2. I look at the equation. For every 1 mole of O2 consumed or used or reacted, I release 572 kilojoules. So using it like mole ratio, I put the 1 mole of O2 on the bottom and minus 572 kilojoules on top. Crunch my numbers and I get minus 286 kilojoules. So heat is released. This is also exothermic, which makes sense because we're still going in this forward direction, which overall releases heat. Okay, this is the end of part 1. Tune in later for part 2.